Gravity versus electricity in the terms of how a star works. What's great about being here for a conference that's focusing on energy and energy production, the sun, every star, is a perfect example of something that puts out an enormous amount of energy. And so we can learn from that. We can study how a sun does it, and then maybe there's aspects of that that we can learn from. Since the time of Newton, we have talked about forces as what changes the world. This is a very simple, elegant formulation which has fueled a lot of mechanistic science for hundreds of years. It's a very useful way to look at the world if you're a scientist. Forces cause change. It would be a much longer lecture to tell the story of how this chart came to be. Those are the forces that are considered in modern astrophysics. The first, gravity, is considered the king. Gravity is considered to cause everything else to come about. We then take into account the effect of magnetic fields, nuclear forces, the weak force. Why has the electric force been left out? I won't go into the why, but it has been. Electric fields, electric currents, not allowed. If you imagine the gravity model, I'll talk us through now the causation through the gravity model. We imagine space with dust, debris, and a lot of emptiness. But gravity is considered to be acting. It pulls together matter. That pulling together creates great pressure, great temperature, and eventually, boom, you get a star. Star is created. Some key aspects of this to highlight. One is the star is all alone in the gravity model. It is separate from the rest of the universe. It's on its own, burning its own fuel. It only came about because of some accident, that there just happened to be enough matter that just happened to come together. And that's it. The star in this model gets all of its energy from itself. Another drawback of this model, though, is that it has never been observed to actually happen in nature and has never been replicated in the laboratory. Another aspect of the problem here is that it violates the laws of thermodynamics, this model. So those are some pretty big strikes against it. What then would happen if we included the idea of electricity, electric fields, electric currents into the picture? It definitely changes the story. What do you call it when you include electricity? You can call it plasma cosmology. Some people refer to it as an electric universe. I don't know if one term is better or not. It is important to know that the Sapphire team were not associated with the Electric Universe group. We're a separate organization, which is fine. They do a lot of really good work. We do a lot of really good work. Let's talk through then what the story would be if we include electricity. What story could we tell about the origin of stars? Again, we have space, but now it's no longer empty. There is no such thing as empty space. Matter is permeated by electric fields and electric currents. Plasma is perfect at conducting electricity. It's the best conductor that we have. It naturally forms into rivers of current. It also naturally supports strong electric fields. These electric fields and currents naturally organize themselves and the matter that they go through. And there is no violation of any laws of thermodynamics. The matter condenses into a variety of localized structures, some of which we know about in the laboratory, such as plasmoids. Others we are learning about by studying the interstellar medium. And the picture is that then stars live along these currents, electric currents. The stars then receive their energy from the space around them, or better to say, from their relationship with the space around them. We still envision a center core, which is made up of a variety of elements, depending upon the star, the history of the star, or what the star's purpose is in the galaxy. In the model, that's the positive pole. Think of an anode. And that's in an environment that is relatively negative compared to the positive. As was said yesterday, we often run into discussion problems when people fight over the word positive and negative. Maybe they're not the best choice of words, maybe we don't understand electricity, but we can do some good physics by talking about it this way. So the surrounding medium is the cathode. in this model. The star lives, again, inside of a larger electrical structure. The plasma will seek equilibrium. There's that separation between the plus and the minus. That creates a lot of motion, a lot of activity. Things try to come to equilibrium, but they don't. They can't. Just like you and me living here, you could argue we're trying to come to equilibrium, but we never do, right, until we die, and then we're in equilibrium. That striving to come to some equilibrium is the byproduct of that, is this immense amount of energy and light that comes from that struggle. To highlight again what I said before, in this model, the star is not creating its own energy. The star is, better to say, transforming energy. And that energy comes about through the star's relationship to the space around it. Its relationship to other stars, its relationship to the galactic medium is the source of the energy. Planets get their energy from the sun. The sun gets its energy from its larger world. We live in a hierarchical universe. There's some blueprint that's being manifested over and over and over that has to do with energy transformation. How do you transform energy from a star to a planet? Stellar energy is way too intense for a planet. Direct stellar energy would fry a planet. It would be gone. So how do you step it down? How do you bring that energy, solar energy, down to a level that a planet can use? Same is true with you and me. If you put us up into the magnetosphere, we would die. Too intense. How do you step that energy then down to a level that you and I can live in, so we can have things like broccoli and hamburger, and we can eat and we can get on? Help me, I'm going off script.
That's fine. You're doing fine. It's wonderfully entertaining. Yes, it was the broccoli part. Yeah.
Can you take over?
Sure.
Okay. Here you go.
This is how it works in the lab. Oh, I got a pointer. Thank you, Michael.